Hi everyone, this is the first video in the Vision Transformer series where we will delve into the evolution of self-attention in images, starting with this paper titled Non-Local Neural Networks. So let's get started. First, let's discuss why we need self-attention in images where convolution already seems to be quite effective. As you recall, the key properties of convolution are local connectivity, weight sharing, and translation invariance. Focusing on local connectivity, it enables CNNs to capture salient features in nearby areas, which is efficient for processing spatial data. However, this approach has a limitation. It struggles with modeling long-range dependencies. CNNs can achieve this to some extent, but typically at the cost of significantly increasing the network's depth. So we are going to see some approaches that can overcome this limitation. There are various attention mechanisms that attempt to address these limitations in different ways. Among these, we find the SENet, Gather Excite, Bottleneck Attention Module, and CBAM for Convolutional Block Attention Module, which are notable for their innovative use of attention. However, it's critical to understand that these methods apply attention concept uniquely, such as through channel-wise or spatial reweighting. The adjustments made by these mechanisms are based on predefined operations, not on the pairwise interactions between pixels or regions. While they are effective in their context, they do not model the direct interactions as self-attention mechanisms do in vision transformers. For this reason, in our series, we will not discuss these algorithms. Instead, we will delve into methods that employ attention based on direct pairwise interactions among pixels or image regions. So in this video, we start with this paper titled Non-Local Neural Networks. You might have seen that this paper and its proposed model is referenced quite often in other papers related to attention and transformers in computer vision. Therefore, it is very useful to discuss this paper in detail. So let's see how this works. As opposed to the local connectivity in convolution, the non-local module computes its output as a weighted sum of the features from all positions in the data. And these weights are computed using the direct pairwise interactions between pixels. As shown in this equation, xi and xj are the input features at position I and j, and for computing output y at position I, we take weighted sum of all features at all j's. There are two important terms here. Function f is a pairwise function that computes the relation or interaction between I and j, and g is a unary function applied to features at position j. And C of x is a normalization factor such that the weights sum up to 1. So C of x is the sum of fxi xj over all the j's. Now let's see how this non-local module is different from convolution, fully connected layer, and even self-attention. First, comparing non-local module with convolution. The most obvious difference is that convolution has local connectivity like in a local neighborhood of size W, whereas NLM considers interactions between I and all the j's. Next, what's the difference between NLM and fully connected layer? There is a major difference here that clearly distinguishes NLM from FC as well. And that is, in NLM, we compute the weights as the interactions between pairs of pixels I and j. But in FC, there are no direct interactions between pixels. Furthermore, NLM can work with variable input size and still maintains the size in the output. Whereas in fully connected, we must define a fixed input size and a fixed output size. Finally, what is the difference between NLM and self-attention? The short answer is that there are no difference. It depends on the choices of f and g, of course, but we can say that self-attention is a special case of NLM. Next, let's see the choices for functions f and g. For the unary function, the authors use a simple linear function shown here as g equals w sub g times x. And this can be implemented simply using a 1-by-1 convolution. Recall that 1-by-1 convolution is essentially like applying a dot product along the channel's dimension. For the pairwise function f, the authors proposed 4 different choices. The first choice is to use the Gaussian function given as exp of xi transpose xj. The second option is an extension of the Gaussian function on the embedded features. So in this case, we first apply these embedding functions theta and phi to xi and xj respectively, and then take the exp of the dot product between these embedded vectors. As we will see, this case is indeed similar or identical to self-attention depending on the choices of theta and phi. The third proposed option for f is a dot product between these embedded features, theta of xi and phi of xj. And finally, the fourth option is to concatenate these embedded features followed by a linear layer and a ReLU activation. This non-local module can be placed in a block in a neural network as shown in this figure. This block receives input feature map x and then computes the embedded features theta of x and phi of x using a 1-by-1 convolution. And these then undergo a dot product followed by softmax. This results in weights which are then multiplied by the result of the unary function g of x to get output y. Finally, we apply another dot product of w sub z with this y and add a residual connection as shown in this equation. So let's annotate this figure, and we can bring these q, k, and v matrices, replacing theta of x with q, phi of x with k, and g of x with v. And now, putting the non-local block and self-attention side by side, we can see the resemblance between the two. This block can be integrated into any existing neural network architecture to capture long-range dependencies in data. The paper has shown the significance of adding such non-local operations in several computer vision tasks, including video classification, object detection, and segmentation. And that wraps up our first video in this series. To recap, we embarked on an exploration of self-attention within the realm of image processing. Our first deep dive was into the influential paper Non-Local Neural Networks, a pivotal piece in understanding how self-attention mechanisms can be applied to images. I hope this video has provided you with valuable insights and a solid foundation for understanding the evolution of self-attention in the image domain. Stay tuned for our next video, where we will delve into attention-augmented convolution and further unravel the complexities of self-attention. Thank you for watching, and see you in the next video.